I'm just going to get right into it. As you can already see, the title of my talk is Journey to the Cloud with Packer and Terraform. So just to get some PR stuff out of the way first. So I work for a company called Box. If you haven't heard of it, it's a modern content management platform. What that means is it allows you to store your files in the cloud securely, share them with other members of your company, or other people in the world as well. So check us out at box.com. So the team that I particularly work on doesn't really care about the Box product ultimately. The team is called Productivity Engineering, and our customers are the 300 engineers that work for Box. Our mission is to make them more productive in any way we can. One of the ways that we do that is we own the continuous integration infrastructure and pipeline. We allow developers to rapidly run their tests and get feedback on them. In light of this, we wrote a tool called Cluster Runner. This will set the context for the talk. What this tool allows you to do is allows you to run your tests in parallel across a fleet of machines. So instead of your tests taking a really long time running serially, if you use Cluster Runner, you can run very quickly. So this is a dashboard showing Cluster Runner in action. The large squares here represent a build, a particular type of test suite that's running. And the smaller circles represent different nodes. All these nodes in the Cluster Runner cluster are supposed to be identical, so your tests can run on any one of these nodes. So the reason that this is important is the purpose of this talk. So just to make sure that everyone's in the right room, how many of you have run or still run bare metal data centers in your companies? So still quite a few of you still. So a couple of years ago on the productivity engineering team, we used to run our CI infrastructure on bare metal. You can already imagine some of the problems with this, being a team that is focused on getting developers to run their tests quickly. So this talk will cover how we took that bare metal infrastructure and turned it and went to the cloud and how we got there. So a couple of years ago, the state of our infrastructure was in quite a bad place. We had these huge fleet of machines that were running entirely on bare metal servers, completely underutilized. There was no concept of elasticity. Once the server was up, it was staying up. If we needed to change its role, we had to use the configuration management tools like Puppet to change its roles. And in particular for us as a CI team, we had a huge problem with host divergence. Now you can imagine you have about 300 machines in your infrastructure. Your tests could pick any one of those machines. If one node is different from the rest and your test fails on that one node and not the other, you have a huge problem and huge drain in productivity for your developers. And finally, this problem is a little bit more specific to Box, but we were heavily reliant on other teams to manage our infrastructure for us. If we needed more servers, we had more developers join us. We needed more servers now. Well, we had to put a purchase order through, and it would take months to get the servers up and running and ready for use. If we needed to re-provision a server, we'd have to go to the operations team and have them do it for us, which often meant that we had competing priorities to deal with. If you worked in an enterprise company, you know that they're always focused on production servers. As a result, we decided to go to the cloud, like any sort of person in this situation would do. At this point, we had sort of two options. We had like all these bare metal machines still ready for use, and then we had like these public cloud options. So we had a decision to make. We had some budgetary constraints that prevented us from jumping immediately to the public cloud, while we still obviously had these huge number of bare metal machines that we could use. So we decided to use a hybrid approach, both utilizing our internal private cloud and some public cloud offering like AWS. The goal was that we would utilize our current servers till they reached end of life. and then any future growth would happen on the public cloud side. Now you're probably thinking that how do you set up your own private cloud when you have no cloud? It takes a lot of work to set up your internal private cloud. Well, this is where this vendor called Platform 9 comes in. It allows you to utilize your existing bare metal infrastructure and get a private cloud going in like days, literally. So we started with this. They do charge quite a bit of money, but it's very, very good to get started with them. You can build around your automation using them, your private cloud automation, until you build out your own private cloud. So in our case, we got lucky as our operations team ended up building out a private cloud for us. So we started out with Platform 9. Eventually, we migrated over to our internal private cloud. So as a result, when we were thinking about this problem, we had to sort of solve for these multiple cloud providers. Obviously, we had the internal private cloud hosted on OpenStack, and we wanted our future growth to happen in Amazon, so we need to support both these clouds. We also wanted the ability to be able to switch to different cloud providers, like use GCP if needed, or build across multiple cloud providers like Amazon, Google, OpenStack, any one of these. So our goal was clear. We wanted to build this abstract system that would work across these multiple cloud platforms. Now, what I mean by an abstract system is we wanted to be able to deploy our infrastructure that spans these multiple clouds. We wanted to do that in an automated fashion. So this was our goal. So just to get some concepts out of the way, I'm gonna spend some time explaining how we went about this problem. So traditionally, when you're running bare metal infrastructure, you sort of use configuration management tools like Puppet or Ansible to sort of configure your machines the way you want them to be. So what that means is that you spin up some sort of base OS, and then you apply your Puppet manifest, or your Ansible playbook, or your Chef cookbook, whatever you want to call it, to that base OS to turn that server into something useful. And if you need to make a change to that server, you would then go back to your configuration management tool, you'll make the change, and then you run that configuration management tool on that existing server. And these servers would be able to run indefinitely. In theory, this sounds like a sound approach until you start scaling up. And you leave these machines running for a very long time. As you probably know that you're, generally speaking, almost 90% of the cases, you don't, probably even more, you don't have the configuration management tool manage the entire machine. You have it manage probably 80% of the machine. You could still have some portions of the machine that are unmanaged. So if you make changes to those portions, the machine will drift from what it was intended to be initially. Another particular problem is if you need to change the role of the machine, it's very difficult to do so because once you apply one role to the machine, it leaves a whole bunch of configuration bits on the machine. To change a different role, you have to do a whole bunch of deprovisioning work, which is very painful. So the natural consequence of this is to not use that model and instead use what is termed the immutable servers model. In this scenario, instead of provisioning just a base OS server, you provision an instance that has everything that you need for a service to run. So you bake everything that you need for a particular service into an image, and you deploy that image as an instance. Now, if you need to make changes to your instance, you don't change the live running instance. Instead, you make a change to your base image, and you redeploy the instance. So you're always starting from some sort of known state, and allows this sort of versioning of your infrastructure. This is sort of quite far-fetched from having completely long-running machines. So there is this sort of intermediate approach that you can take, which is referred to as Phoenix servers, where you still continue to run your configuration management tool after server is up. However, you redeploy your instances from scratch a lot more often. What this shows you is that your Puppet manifest or your Ansible playbooks can indeed build a server from scratch, and that your infrastructure or your services will still run when they're torn down on a frequent basis. Eventually, if you're doing this enough, you can set goals like, I'm going to do this weekly, I'm going to redeploy my infrastructure weekly, and then get to the point of daily, and so on. If you're doing this enough, you just automatically get to the immutable infrastructure model because you're doing this so often. Generally, Puppet runs, for example, once every hour. If you are just redeploying your infrastructure every hour, there's no need for Puppet anymore, for example. So this is the approach that we took. We were like, OK, we're going to build these fully baked images, but we're still going to continue to run our configuration management tool like Puppet on them, even after they come up. But eventually, we want to get to the point where we can completely go to immutable model. So obviously, we needed a way to build images and verify those images. You don't want to just start building images and not have them some sort of sanity checks on them to make sure that they are what you expect. And eventually, you want to deploy instances from those verified or approved images. So for logical purposes, we decided to call the building and verification of images as phase 1 of our project, and the deployment of those instances from those images as phase 2. So we also set some sort of arbitrary, I guess, requirements. Being a productivity engineering team, we wanted this system that we ultimately will build to be used by other developers at Box to sort of build their own sandbox environments and allow for experimentation and that sort of thing. So we wanted such a system to be easy to use and self-service. We also wanted it to be fully automated. What I mean by fully automated is, say I have a Jenkins node that I'm bringing up using the system. I want the system to be automatically attach that Jenkins node to an existing Jenkins master where I tell it. So I push a button and this just happens. This is sort of what our ultimate goal was. And of course, I've briefly touched upon this. We wanted the system to have built-in validation. That goes without saying. So let's sort of get into it. How did we go about building and verifying these images? Well, thankfully, there's an open source company called HashiCorp that sort of specializes in this sort of thing. They have a tool called Packer, which abstracts away the OpenStack APIs and the Amazon APIs and the Google APIs that allow you to build images very easily. I'm sure you'll hear more about Packer. But the thing that I really liked about Packer is that there's multiple clouds that it supports. It's very easy to start today with OpenStack and Amazon, and then later on, you decide that Google is offering you a better deal. So you can switch gears and go out and try for Google. Another really important thing was the fact that Packer allows you to use your existing Puppet manifest, Ansible playbooks, chef cookbooks, and recipes without having to change them. This is very important. As you're doing something a certain way for years, you don't want to rewrite your entire configuration management system into something else. So this is very powerful. It allows you to do this out of the box. You can get up and running very easily. So great. So we're almost done here. Well, what we realized was Packer is sort of built for people that are working with images on a day-to-day basis. And this is like a sample Packer JSON file. And this is sort of like hard to follow if you're just getting into Packer. We wanted to abstract some of the complex bits away and make it easy for developers to use. I'm just going to run through this file quickly just to highlight the different sections, and then I'll talk about how we solve this. So this is the provisioner section. In this case, this is a shell provisioner. What I'm doing with this provisioner is I'm installing Python 3.3 using yum. Of course, this could be any type of provisioner. I could have the Ansible provisioner, Puppet provisioner, whatever I need to build my image. And I'm saying that I want to ultimately build the image that I'm building into OpenStack, as the builder name specified there. Notice how the credentials for this OpenStack instance are specified in the Packer JSON file. We didn't ultimately want developers to have to care about these sort of details. We just wanted them to have an image. So we decided to write our own tool on top of Packer. The cool thing about Packer is that you can easily automate on top of this. It's very easy. There's JSON files everywhere. It's very easy to automate. So the way that we decided to solve this problem was we just thought about how a developer would think about this. I have a source image. This could be a base OS image. This could be some other image that someone else put relevant packages in. Then I want to run a set of provisioners on that image. And I want to bake that image into a complete image that I can then use to deploy instances from. Then I want to run some verification steps on that image. And I want to ultimately end up with this verified image that I can actually deploy, that I feel confident in. The portion that Packer didn't supply out of the box was the verification step. Like with Packer, you can use provisioners to exit non-zero and do some sort of verification right when you're building the image. However, what the verification we wanted was, we wanted to actually bring up the instance separately from Packer and run the validation checks then. Because we ran some post-processing steps on the image. We edited the image, compressed the image, those sort of things. So the image was sort of fundamentally different from when Packer was building it. So this verification sort of happened after the image is already complete. So instead of Packer JSON file on the left, this is obviously a simplified version of the Packer.json file. There's a lot more going on there. With our tool, which is built on top of Packer, internal tool, we simply specify 3 lines of YAML. Notice how you have a source image section. You have a provisioner section. This is a list of provisioner section. These individual provisioners are just what you saw earlier. These are just separate files with a provisioners section that Packer expects. Now you have the power to reuse these provisioners for different images as well. You can just, it's in the same repo, you can just embed it in your image definition. That's what we call this YAML file. And of course, you also have a verifier section now, which is separate from what Packer provides. And of course, you can also reuse these verifiers as well. These verifiers also follow a similar format to the provisioners, and they run separately. All right, so instead of invoking Packer using the standard Packer build, packer.json, we simply invoke image pipeline build. We specify the name of the image, and then we pass in the builder. Image pipeline is able to use the same image definition and build across whatever clouds that we support. Currently, OpenStack, AWS. So if you wanted to build the image, same image definition, pass it in to image pipeline, it uses Packer underneath, and you got your image. We store all these configurations for images in a repository. We refer to it as Packer image config. This allows us obviously to version control the definitions, allows us to add CI to this stuff, allows us to code review this stuff. So it makes it very easy to manage. I'm just going to go over quickly the directory structure of this repository to get an idea. Of course, you have an images section. This is all your image definitions. And you have, you have a provisioner section. These are all the list of different provisioners that you can use. And you have a verifier section. These are all the list of verifiers you can use. So it's pretty straightforward. The way that we call image pipeline is using these Jenkins jobs. And this simply invokes image pipeline for different clouds. And what it does is it periodically builds these images. So we say that this job runs every hour. Give me a new image now. And you will get like a list of these verified images. If an image is not verified, it won't get built. So ultimately, we'll only have verified images on our cloud. So just to summarize, these are some of the benefits that we saw from writing abstracting on top of Packer. We have obviously abstracted credentials. That's a little bit more user-friendly. We have some validation now. And we have the power to reuse our verifiers and provisioners. OK, so earlier I showed you the slide where we divided up phase 1, phase 2. Thanks to image pipeline and Packer, we can call phase 1 complete. We are continuously building these images. So this part is very important. The symbol that you see here, the circle symbol, it implies that we're continuously doing this. This is very important. You want to continuously be building and verifying images. This is only successful if you're doing that on a continuous basis. You don't want to just do it once and be done with. All right, let's turn to how do we take these verified images. Right now I've done nothing useful. I just have a bunch of images. There's no real infrastructure. Now we want to turn those images into actual infrastructure. And again, HashiCorp comes to our rescue. Terraform, which is a lot more powerful than just allowing you to create instances. But one of the uses that we found from it was that it's able to create instances across different cloud providers. I'm sure other talks will make you learn about Terraform, all the power that Terraform has. But for this talk, I'm only going to focus on the part where it allows you to create instances. So what we do is, now I have this verified image, let's say in OpenStack, QCOW2 image. I feed into Terraform. Terraform allows me to create this instance. Not only that, Terraform also allows me to do some initialization for this instance. What this means is, if I need to add this, the instance that I'm bringing up to some sort of pool, I can do that with Terraform. If I need to set the host name on this instance, anything I need to do that can't happen as part of the image itself, that has to only happen when the instance is coming up, I can do with the Terraform provisioners. And I can do this for any number of instances that I need. Now that one OpenStack verified image can turn into hundreds of actual real instances. So now you're already starting to see the power of this immutable infrastructure sort of model. Not only that, if I decide to go to Amazon, I can use the same process, and now I can have n instances running in Amazon. So similar to what we saw earlier with the Packer.json file, we also found the Terraform configuration format to be very specific to people that are using Terraform regularly. I'm just going to point out some of the sections here. You have a provider section. This shows you that I'm using Amazon as my provider. If you had OpenStack, then you'd use OpenStack as your provider, and you pass in some credentials. With Amazon's case, of course, you have access key, secret key, and region. And then you have a resource section, which defines that I want an AWS instance of a particular type. In this particular example, I want 100 of these Jenkins node type instances. Now, pay particular attention to this provisioner section. I am calling a shell script to add a Jenkins node. What the Jenkins node is this instance that Terraform is creating, and it's attaching to this jenkins-master.box.com and applying the label Python 3.3 to it. This provisioner will be the same whether I'm deploying this instance in Amazon, Google, or OpenStack. I just want a Jenkins node attached to a Jenkins master. So there's a chance for reusability. With Terraform, I would either have to use the module structure, or I would have to duplicate this code in the OpenStack configuration. To simplify things a bit and to sort of fit our model, we decided to automate again on top of this and abstract some of these bits away. And we wrote a tool called Terraform Configuration Generator. So again, we can express our definition in simple YAML. You have a provisioner section. You say, I want a Jenkins node. This will take templated provisioners and pass in these variables that I'm specifying here. My master is jenkins-master.box.com. My label is Python 3.3. And any provider-specific configuration can go in the provider section. I want 100 of these things in Amazon, and I want 50 of these things in OpenStack. I just specify the AMI I need for Amazon. I specify the image I need for OpenStack, and I'm good to go. This tool will simply generate out the Terraform configuration I need for both clouds, which is ready to be fed into Terraform Apply. So this sort of speeds that process up. Again, we store these configurations in our repositories, in a repository once again. Again, same spiel about version control, CI, code reviews, all that good stuff. I'm just going to once again point out some of the directory structures, some of the interesting elements here. We store all of our definitions. These are your YAML definitions like the one you just saw in a definitions directory. This allows other people to take a look at what definitions look like and reuse them if they need to. Any actual Terraform configuration files go in the generator directory. And finally, the templates house any reusable provisioners. So when the configuration generator tool runs, it will take the templates, it will pass in, it will resolve the necessary variables, and then it will generate the necessary files. Okay, that infamous slide once again. Now, with phase 1, we had image pipeline. With phase 2, we have Terraform. And again, to harp on the importance of doing this over and over again, you don't want to just spin up 100 Jenkins node instances one and leave them running. That means you got nowhere. You want to be able to recycle, refresh your infrastructure on a regular basis. And we did this with our aptly named recycle project in Jenkins. What this does is you pass in the Terraform definition file that I just showed you, and it will figure out that, hey, I've got 100 instances of this type in Amazon, I got 50 in OpenStack. I'm going to take them all down, and I'm going to bring them back up with the latest image. So this is the purpose of this project. So just to sort of illustrate where this is, in one use case, I guess, where this is useful. I have a Jenkins cluster that's very happy. Everything is running. All my tests, all the developers are getting consistent test feedback. All of a sudden, there's a rogue test that, say, corrupts a Git repo on one of the machines that is shared. All of a sudden, my entire infrastructure has gone bad due to this one flaky test. I figure out the test, I fix the test, but my infrastructure has still gone bad. Now I have to figure out to uncorrupt the repo using MPSSH or something, right? Like, or say this was like a long-running services. I have to actually fix the problem when I already know what happened. I already know that this was a bad test. We already fixed the test. My infrastructure is still in a bad state. Well, thankfully now, I just simply push a button. I say, hey, just rebuild this thing for me. Just grab that's the latest known image from a state that you know, and just let me know when you're done. And what you'll start to see is this recycle project, it will smartly take a certain percentage of your infrastructure. It doesn't want to take the whole thing down. It wants to take down in stages. So over time, you're just literally waiting for this to happen. You're not actively doing anything. You're just watching things restore itself. And over time, your entire fleet returns back to normal. We do this on a nightly basis. We recycle our entire infrastructure on a nightly basis to always start from a known state. We want to get to the point where we don't have to worry about nightly. We just do this all the time. So as you can see, we've gone a long way. We started from complete bare metal infrastructure, long-running single-purpose machines, and now we're at a point where we can, with one button, we can recycle our entire infrastructure. So just to sort of illustrate some of the lessons that we learned with this, so one of the important things, I think HashiCorp also mentions this a lot, is you don't want to treat your infrastructure any different than you treat your other software projects. You want to interact with them via an API. You want to version control your infrastructure definitions. This is critical to be able to get to this level of automation. You also want to make it very easy to be able to build images and verify images. That has to be a very easy process because you want to be able to repeat that as many times as possible. And I think I already mentioned this. You can use the power of these sort of tools, these infrastructure-focused tools, and automate on top of them. You can take those tools, use them as the backbone of your projects, and then build your own customizations on top of these tools. So we're in a good state now, but we want to continue this further. We want to get to another level of automation. In particular, our team is focused on is a CI-focused team where we have a lot of infrastructure that is used at certain hours. So during the day, our infrastructure is heavily utilized. At night, it's almost idle. It's barely used at all. So auto-scaling is a perfect use case for us. We've already started investigating into this, how we can leverage auto-scaling and only use infrastructure when we actually need it. We can double the capacity during the day and completely almost go to zero during the nighttime and save a lot of money for our company. Just along those lines, we can also start looking into containers to solve some of these problems. What containers, the difference between virtual machines, one of the primary differences is containers boot up time is very low compared to virtual machines. Now, even if you're spinning up just one virtual machine, you still have to wait for the OS to boot up, and that can still take anywhere from like 5 minutes up to even probably further. You can do the same. You can probably spin up 100 instances in those 5 minutes, but you still need those 5 minutes. With containers, you don't have this problem. You can instantly spin up a container. So for a team that runs tests, there's a use case here where you can just spin up a container, run your test, and delete that container. So you're only utilizing your infrastructure for when you need it. There's no more efficiency than that. You literally tear it down, you run your test, you tear it down. And that's the level that is completely feasible in today's world. So that's all for me today. Thank you all for listening.
We do have time for a couple of questions.
Yep. Yeah, if you guys have any questions, let's hear them. Is there a mic? Or?
So forgive me if you answered this already, but you mentioned the Terraform configuration generator, which sounds really cool. It sounded like you used that instead of the Terraform modules, like that architecture.
Yeah.
Could you talk about why you decided to go that route?
Right. So we for our use case, we tried the modules portion, but what we realized with the modules portion was we were still duplicating a lot of the provider-specific fields. Like you probably noticed that in the Terraform definition, there is no area where you specify, I want this username or this password, I use this variable. With modules, we realized you still have to do that. So that was one of the reasons we did that. And also, we thought that the way that the Terraform configuration generator does it, it was very easy to follow for someone, where they're like, okay, I have a Jenkins node provisioner that I'm using, and it's right there. With modules, you had to sort of, there's a lot of backtracking with paths. And so those are some of the reasons that we decided to switch to a generator. Any other questions?
So I'm just curious as to how you handle when you spin up and spin down your infrastructure, like IV cache, like build tools, caches of jars and things like that, because that can add minutes to builds if you're spinning up a fresh machine, I can imagine.
So that's a really good question. So the way that we solve some of these issues, like of caches or large sort of packages on the machines, we actually just pre-bake them into the image. So for the IV cache is a perfect example. We have a job that runs every night, updates the IV cache. We pull that IV cache into the image itself. So this is happening asynchronously. So you don't have to. This is not happening when you're building the image. This is happening on the side. You take that IV cache, you put that into your image. Now all of a sudden your IV cache is up to date, and you don't have to wait for things to slow down for you.
Just to kind of follow up on that question in particular, for certain things, I imagine if you have any of these machines that are running with secrets or whatnot, that would be something you wouldn't necessarily want to bake into the image, or perhaps it is. How do you handle that sort of information? So,
I guess it depends on where you're building the image. For us, we build the image exactly where it's going to run, in the environment it's going to run in the. So if you're building the image outside of your secure environment, then I can see that issue arising. But we're just building the image in the exact same environment where it's actually going to run, so we have no such issues with that. Any other questions?
You spoke about verification. Just wondering, how would you verify the images after it's built? Like, would you have a state that you want to verify against, or how does that work?
So I didn't touch on this in the talk. The way that we actually verify images is, you know how ultimately when we're deploying the instances, we use Terraform to deploy the instance. The verification step actually invokes Terraform to bring up the image itself. And then in that, we just use Terraform local exec provisioners to do verification steps. Remote exec provisioners, where it actually logs into the machine. And it's like, is this service running? Is this file present on this machine? Is this package present on this machine? Those sort of checks.
So to build on that, is there a policy that you could build that you have in place that after that policy, is there like a, kind of like a policy that Terraform would follow to say, all right, verify that maybe Apache's running your MySQL? Like, how does it know what to verify?
Right. So I mentioned those the verifier section in the talk. So that just specifies what you're verifying. So you'll have a list of verifiers. If your image needs those verification steps, you just tack that on there.
I think we've got time for just one more.
Any more questions?
We covered them all. No? All right, can we thank our speaker one more time?